Goldman Sachs engineers don't just make things. We make things possible. Our engineers are innovators and problem solvers, building solutions in risk management, big data, mobile, and more. Interested? Find out how you can make things possible at goldmansachs.com/careers.
Hello and welcome to the InfoQ podcast. On today's podcast, we're talking to Ben Kehoe. Ben is a Cloud Robotics Research Scientist at iRobot. In addition to having probably the coolest title of anyone I've spoken to on the podcast, he's also been a champion of iRobot's use of serverless in the AWS cloud. He has previously spoken on serverless at past QCons and other places like ServerlessConf. His videos can be found online, again, both at QCon and at ServerlessConf. Today, we'll be talking about what prompted iRobot's move to the cloud, what made them choose serverless, some of the challenges with going serverless. In particular, we'll discuss some of the gaps between services that are available in more traditional applications development and in the serverless architecture itself. We'll discuss strategies for going serverless and what to watch out for with your next serverless deployment. Thanks for joining us on the InfoQ podcast. Ben, welcome to the InfoQ podcast.
Thanks for having me.
Ben, what does a Cloud Robotics Research Scientist do?
Well, it's a very buzzwordy title, and it would only get buzzwordier if I added serverless to it. But Cloud Robotics is fundamentally about using the internet to enable robots to do more and better things. So giving devices access to massive computation in the cloud, giving them access to large databases of information that allow them to make better sense of the environment that they're in. There's multi-robot learning. So when one robot encounters a new situation and learns from it, you want all robots to get smarter because of that. Those are some of the techniques. Also, it enables you to connect robots to humans when the robot can't solve the problem on its own. There are lots of these aspects that the cloud can bring to robotics to sort of level up the capability of robots.
So let's kind of start off and talk about 2015, 2014. You had a product, I believe it was Roomba 980, and you made some architectural decisions that led you down a serverless route. Take us back there. What did that look like and why serverless?
Yeah, so I joined iRobot in 2015, and as a cloud roboticist, I work with, how we can use the internet to enable robots to do more and better things. And iRobot was attractive to me because it has the most robots. For a cloud roboticist, scale is important. And that was in the midst of the run-up to launching Roomba 980, the first connected Roomba from iRobot. And at launch, we were using a sort of turnkey IoT solutions provider. So that was dealing with all of the connectivity pieces, sort of the back-end cloud side, firmware update, delivery, all of those pieces. And we had realized even before launch, while the provider had been chosen, a few years before for reasons that were probably valid at the time, it didn't have the scale or the extensibility we needed. And so we were looking to move off that platform onto something else. And so we had decided that we wanted to own, sort of the back end on the cloud and own that capability as part of core technology piece for iRobot. And we wanted to choose a new connectivity provider that would allow us, that manages the connections from the robots to the cloud. We had decided that we wanted to be on AWS for that backend. And it turned out that AWS IoT, which was launching then, was a good choice for that connectivity layer. And for iRobot, we're historically a device company. And while we have experience with networked robotics and some cloud-connected robotics, we hadn't really done cloud-connected robots at the scale of Roomba before. And we really didn't want to be in the business of building scalable cloud applications. That's not what we do. We make robots, and we want to focus on that. And AWS Lambda had just come out. AWS IoT is serverless offering. There are no scale knobs to tune. And so we said, we looked at the AWS services that were there and we said, we think we can build this without actually having to run any servers or any containers. And so we sort of went all in, and we were able to do that because switching off of that turnkey solution provider, we didn't have a legacy application that we were trying to port. It was essentially greenfield. And so that was a real powerful enabler for us to do this, but allowed us to take on a very complex project and deliver that in a timely fashion and then with a small development team, and then continue to operate it with a very small operations team.
So just to kind of draw big boxes, then you had these robots that were out there. You had AWS IoT as kind of like managing the connection between them. And then kind of backing the AWS IoT, you had serverless functions with AWS Lambda. What did it look like after that?
So we currently use, depending on how you count, 30 different AWS services in production as part of that single line of business application, which I imagine that has to be, one of the higher amounts of services that people use applied to a single problem. I think there are probably many organizations that use a lot of AWS services across a lot of different applications in their business. But that's really powerful. And, we made a decision early on to not be afraid of using services and, for example, become very comfortable with CloudFormation custom resources, because not all of these services have CloudFormation support or support in the way that you want to use it. We found that very quickly what it required to be serverless native and to stay serverless was sort of bending everything to your will, taking the services that are out there and saying, okay, well, how do we use this to accomplish the problem? Rather than saying, well, what's the ideal solution to this problem? Let's choose a technology that's closest to the ideal. Let's choose a serverless technology and figure out how to make it work. How do we duct tape it together with AWS Lambda to accomplish the problem?
So is it like an event stream that each of these devices are putting events onto a stream that's going into Kinesis via serverless? Is that kind of like the overall architecture, or is it persistent connections actually doing things?
Yeah, so AWS IoT provides, it's an MQTT based solution, and that's a IoT protocol. And so the devices have a persistent connection to the cloud that's bidirectional. So we can push data down to the robot can push events back up. And for the most part, events are related to device lifecycle. So when a Roomba starts a cleaning mission, it starts transmitting some data about what it's doing, what stage of the cleaning cycle it's in, all of this stuff. And then at the end, it sends up a report that says, this is all the things that I've done. And on our robots that support systematic navigation, it also sends up a request to say, hey, I want to upload this map that's too big to send through MQTT. It's, a couple megabytes in size sometimes. And so we want to do that via file upload. But it doesn't have the connection to AWS IoT is authenticated using certificates. It actually uses the TLS connection to the cloud to mutually authenticate client and server, which is really nice because those certificates are then signed by iRobot Certificate Authority that then we prove to AWS that we own. So we've registered that certificate authority with AWS, and any robots that are connecting that have our certificates on them can then connect to the cloud. So we don't have to, in our manufacturing process, go through a step of batch sending all of the robot identities to AWS. We just send the authority that signs them once, and then our manufacturing process is disconnected from AWS, which is really nice. Because when we switched over, we had robots in the field whose cryptographic identities we didn't record at the factory. And just having a logistical chain from manufacturers in China all the way to US East 1 is a long chain to maintain. And if anything breaks in there, people couldn't register their robots. So that's not something we wanted to have. And that was a key choice in selecting AWS IoT, because it allowed you to bring your own device identities, which since then has become a feature of more IoT cloud providers, but it's pretty important logistically. So what they don't have is standard AWS credentials. So when you want to do an upload, you can't just have the robot authenticate itself to a service like S3 to do the upload. This is where pre-signed URLs come in, which is a URL that contains temporary credentials that the cloud is creating. So it can send that entire URL down to the robot and say, here, you can go upload your file. So then the robot uses that URL, which is opaque to it, and says, okay, I'll do an HTTP put. And so that's how we upload, sort of larger files. And then based on that, right, then we can receive events from S3 about that to say, okay, now we've received the upload. We can indicate that in the mission record so that the app can know that there is a map to be gotten, right? So all of it happens in a very event-driven fashion, which IoT in general is pretty event-driven. and therefore is sort of a natural fit for an event-driven architecture, which is also a natural fit for serverless architecture.
About 9 months ago or so, I did a contract. It basically was help a company do some geospatial queries, and I basically helped them work out a serverless solution for it. And as I was working with this and kind of prototyping a solution to help them with this particular problem, I started working with serverless and found all kinds of little gotchas as I was going through the things that I just like didn't intuitively expect after building lots of what I'll call traditional applications. So this podcast is really to kind of talk about your experience of doing the same thing, but just obviously at a much higher scale than what I did. And not only those kind of initial problems that you all had to solve circa 2015, but what you've had to live with over the last few years and where this whole serverless approach to developing applications and architecture may be heading in the year to come. So that's kind of that main area that I wanted to focus on with this podcast. What are some of the gotchas? Like if you're going to develop an application that, as you were talking about, has this stream of events that are going through there and is responding to those events and allowing you to do other things like uploads and being able to do some processing. And then once that's done, send other events that are being fired. What are some of the things that you need to think about or some of the things that you'll have to face?
I think there's a couple. There's always, when you're serverless, you're using managed services in preference to building or running your own software whenever possible. And that means you have to sort of accept the limitations of these services as they exist. So a consequence of that is, until very recently, Lambda didn't have an SQS integration. And so if you wanted to use SQS with Lambda, you had to go through, a process of setting up a recurring event that invoked a Lambda to query the queue and then dispatch messages off it to other Lambdas, which worked. And it was a pattern that you could sort of nicely tie up into a CloudFormation custom resource, but it certainly isn't elegant. And so there's a lot of things about going to war with the services you have, not the services you want, that you don't end up having as much when you have more control over the software that you're putting on the cloud. So for us, it's meant we use basically exclusively DynamoDB as an operational store. So we don't use RDS for even data that is pretty relational in nature. We store it in DynamoDB and then do the join on the client side in the Lambda. And the reason for that is that there's no HTTP interface to RDS. And so maintaining a database connection in a highly scaled out Lambda can often choke your database, and your cold start times are high because you have to set up a database connection. And so those are, architectural choices that are, in the small scale, narrowly scoped to just that choice limiting. But taking, serverless is all about looking at the total cost of ownership across not just your development time and your bill, but also your operations, the amount of people that you need to do it, your time to market, all of these pieces.
That was actually one of the questions I was going to ask you is like that boundary between a highly scalable elastic resource like Lambda and something like RDS that may not be elastically scaling at the same level. What did that boundary look like? So your choice was just to stay away from that problem.
Yep.
Good choice.
Yeah, and at some point, if they add an HTTP interface, so this happened with Athena. Athena launched with just a JDBC connection as an interface and now has HTTP. I mean, we really like Athena, but it was much harder to use with Lambda beforehand. And so we didn't really dive in earnest until I got that update.
Okay, so let's kind of walk up just the stack. If you're going to deploy a serverless solution, the first thing you've got to think about is your environment, right? You write a function. That function, if you're working locally, you might be able to get that kind of running locally. But what about like dependent resources that are cloud-based? Is there a way that you deal with that? How do you deal with like this whole suite of serverless functions that you're developing? It's got to be on the cloud, right, for it to work.
Well, yeah. So I also think that in the ideal case, the amount of code that you're writing is minimal. And so the function development is not actually the primary focus when you're creating serverless architecture. It's the services, how you're wiring all together. One of the things that I realized recently was that if you're comparing an architecture that's using Lambda for all of the computation, but accessing databases and message queues and authentication that's all running on Kubernetes, that's less serverless than a system that's using managed services to do all those other pieces and has its computation running in Kubernetes. The overall system where your code, which should ideally just be your business logic, right? The stuff that you have to create out of whole cloth should ideally be only the things that you're doing different from everybody else. And so, for us, the starting point of creating a service is CloudFormation and not starting inside Lambda. It's figuring out what are the blocks that I need to wire together to produce. And then in there, where do I need Lambda? Okay, what code goes in there? So then once you're in Lambda, the route that we've taken is to say unit testing happens locally, but integration testing only happens on the deployed system. And the reason that we've done that is that essentially you can't, for us, the choice of saying we want to be able to use any service that we need to. We want to not shy away from saying, oh yeah, let's use that one that solves a problem for us, means that we can't rely on them being locally mocked. That's just not feasible. And so integration testing can really only happen deployed. On the other hand, unit testing, we've taken the approach that we can, so we're a Python shop, and we use a library called Placebo, which hooks into the AWS SDK and allows you to record and play back SDK calls. So for unit testing, what you do is you've got your Lambda set up and makes SDK calls in it, and you run it, and it hits the actual cloud services using, say, your credentials, and records the result of that. So the database output or whatever from DynamoDB is there, and from S3 and from SNS, and all these things are in there. And those go into files. And then for unit testing, you switch it into playback mode. And when your code runs locally and the SDK call is made, it doesn't actually go out to the cloud. It hits that file and loads up the result that you got. And that means all those unit tests can run locally without ever touching the cloud, without actually having to mock out anything, and without having to abstract over those SDK calls, because it's using the SDK's hooks itself. And so we really like that. Now, on an individual developer basis, some developers are really big on writing very extensive unit tests and then doing, sort of a little bit of integration testing at the end to just make sure that everything all works together. Other developers like to write fewer unit tests and do a longer cycle of integration testing. And we've found that both of those work. It's really kind of down to personal preference, but it still maintains that local unit testing, deployed integration testing.
That really is a compelling story about unit testing, because I definitely had issues unit testing the solution I was working with. And integration testing only in the cloud makes total sense. But what about getting to the cloud? What was that experience like? I'm assuming you didn't go to the interface and upload jars manually. What did that experience look like? You said you were CloudFormation first.
When this started in 2015, there weren't a lot of options out there. The serverless framework existed. It was called JAWS at the time. And we looked at it and we said two things. One was the capabilities that it had, in total did not meet our needs yet. It had a plug-in system, so we could have sort of started to extend it. But more fundamentally, at the time, its paradigm was local coordination of deployment. And it was doing that for speed. So it was saying on the developer's machine, the tool should go and actually set up all the resources. And we prefer a cloud deployment strategy through CloudFormation, where the developer says, in a single, more or less, API call, here's the thing I want on the cloud. And then the developer can close their laptop and everything still happens. Terraform also has this problem, right? There's this local TF state file that could be on a CI/CD server somewhere, but is still, needs to be managed by the client rather than the provider. And so we like the approach of let's use something that's a service that handles all this stuff for us. At the same time, that ties you to what the provider has made available. And so we very quickly became accustomed with and proficient at CloudFormation custom resources. We've made some of those libraries that help us open source. And, now just recently, CloudFormation Macros got announced, which is a cloud-side transformation of CloudFormation templates, So we built up internal tooling around this, which essentially does that, right? We allow developers to write, with some syntactical sugar it ends up looking a lot like AWS's SAM tool to sort of abbreviate the amount of CloudFormation you need to write. And then you run it through a transform that expands it out into something more verbose and, with defaults and things like that. And now that's possible to do cloud side. So these macros or transforms you could install as an infrastructure level piece, as an organizational piece to say, these are the things that we allow our organization to do or that we provide to our organization. And then developers are using very lightweight local tools to do their deployments.
With big old CloudFormation scripts. In fairness, I think, I may be wrong, but serverless framework today uploads CloudFormation scripts, right?
Correct. They eventually came around to the same view that we started with, which was a good validation for us. But yeah, it meant that, when we started down the road, and our tooling is still, has a lot of advanced capabilities that are partially unique to us and partially I'd love to see in the tooling at large. One of the things we do is allow, often you want your data sources, your long-lived resources to live separate from your short-lived resources, even within the same service. So you want your template that contains your function code to be separate from the template that contains your databases, because databases never change. They may be defined even outside CloudFormation somewhere, especially in a disaster recovery scenario. So we allow developers to define in a single template all of the resources that they need. And then when we deploy it, say, oh, this one that I've defined in here, this DynamoDB table, that's actually exists somewhere else. Just include a reference to it inside the template.
So everything we've been talking about is the easy part. It's getting into service in production, right? But once you get it there, now the challenge starts. What are some of the realizations, I guess, about running a serverless architecture? Like, for example, you were talking about these functions that kind of are part of this CloudFormation orchestration, that this is the code that goes in each one of these little pieces. But now you've got to be able to trace through that. You've got to be able to understand what's happening through that. What are some of the realizations that you all had once you got this architecture up and running, particularly at scale?
Yeah, so we definitely rely on logging as a mechanism. We tend to package up the information that a function is taking on into a structured record that we're outputting into CloudWatch logs. And then we can use a tool, we pipe all that over to Sumo Logic, and then we can sort of dive in using that to trace executions. A lot of the difficulties we encounter tend to be closer to the edge in the, sort of interaction between robot and cloud. And so they tend to be less about, what's happening in a complex execution trace cloud side and more about what's happening in the messages between the robot and the cloud. And so those are a little easier to pick off and recognize. So we don't have as many of the sort of extended trace situations. We've definitely found things that we expected to have to take on as sort of architectural operational concerns that didn't materialize. So we thought we'd have to build circuit breaking logic in for handling providers' service outages. But it turns out, when you run a hyperscale cloud provider, you build your services in a way that can deal with customers not worrying about, how easy or hard it is for you to come back up after an outage. So we don't have to do that. We allow our Lambdas to point at the service that they want to talk to. The SDKs do exponential back off, and our Kinesis queues back up. And then when a service comes back online, the queue's empty, and it's all just kind of fine. So you sort of only need circuit breaking logic when you're forced to be a good neighbor.
What about things like rate limiting and preventing just like something from pounding one of the services because it had a runaway? How do you handle things like that?
Yeah, and for that, again, our primary situations tend to be around robot side concerns where, an individual robot is being too chatty or something. All those concerns tend to be focused primarily within the AWS IoT service, which provides sort of unique capabilities for dealing with individual clients. Because they're uniquely identified, we can say, oh, this robot is misbehaving. We can actually, blacklist its certificate. Those kind of things are capable in there that aren't as available in more general web application kind of scenarios.
What about, say, something like service discovery? How did you address that?
So that was one of the first questions that we encountered was the client-side service discovery. So, for a robot or an app that's talking to the cloud, how are we routing them to the appropriate services, which is separate from the cloud-side service discovery, which is how do the individual microservices in the cloud talk to each other. So for that client-side service discovery, we decided to go with a red-black deployment paradigm.
So you said red-black deployment. Red-black and blue-green can be used to mean different things in different places. Can you explain what you mean when you talk about a red-black deployment?
We think of it as blue-green means you have you're keeping your load balancer, your endpoint, and you're updating, sort of workers behind the load balancer, which is what happens, when you update a Lambda is you're still calling the Lambda by the same name, but the code that gets invoked when you say invoke that Lambda is changing. Red-black is standing up completely separate copies of the infrastructure, including that load balancer, and having the client transfer who they're talking to from one to the other.
Okay, and so you went with red-black, so the client was actually having to discover and call the correct service. Why that?
We decided to go with red-black for a couple of reasons. One is that it doesn't actually cost anything. When you're serverless, you can stand up an entire new copy of your system and it doesn't cost you anything to have it sit there. And it allowed us to do some integrations that eliminated, primarily it's a cost optimization to keep from having Lambdas calling Lambdas, but it also eliminates the cloud side service discovery problem. So we essentially have a set of microservices that comprise the application. And on deployment, we sort of stitch them all together to remove, from a Lambda that needs to access information in another service, instead of going Lambda to API Gateway to Lambda into DynamoDB, we essentially move the code that would have been in the service that's getting called over into the calling service. And so the Lambda is able to access the DynamoDB table directly. I sort of think about this as it's microservices in code. Like if you look into the repository, there's, very clear isolation of the functionality. But during the deployment process, it essentially mixes all of that around in a way that deploys as a monolith.
Okay, so I'm curious, what was the design decision that kind of made you decide to flatten it like that?
The functionality that we provide for Roomba today, we don't charge for. And so I like to say that the better the electrical and mechanical engineers do their jobs, the longer our robots last and the more the cloud engineers cost the company. So we have to think about how do we bring down the cloud cost as much as possible, because Roombas last for years at a time. There are people who still have first generation Roombas puttering around their houses. That's kind of a scary prospect when you add that cloud cost up per robot per year.
Yeah, this is a software podcast where I'd be asking what's the economics of something like that. As a software developer, I don't get the economics, but it obviously works somewhere.
Well, and it was a very interesting initial transition from, that turnkey IoT solution provider. When you go to those, they tend to charge per device per year. So they give you a fixed cost for whatever your usage is, and you get a contract with them for that. AWS is all pay per use. And going to the purchasing folks and saying, this is what the cost is likely to be. It depends on exactly what the usage patterns are and all those things. They're used to buying parts, signing contracts for parts and hardware that they know their costs years in advance. And this pay as you go, which for us, cloud software developers is like, oh, it's great. Like you're only paying for what you're using, is this paradigm shift for, a hardware manufacturer to think about in terms of cost forecasting.
Yeah, I was a contractor for government agencies who have to have like, what's the bottom line price before we can do things. And trying to talk to them about cloud was an interesting discussion because you couldn't give them an exact price. You give them a forecast.
Yeah. And sometimes, it's better to say, I'd rather pay more for something that I'm sure of.
That's exactly what they said. And I never quite understood that. So I want to go back to this deployment process. Can you tell me a bit more about this flattening process? I'm really curious about it. It's not an approach I've specifically heard before.
So essentially the way that we do this is, every service provides an SDK, and we can do this because we're Python across the entire thing. And normally, a microservices SDK would be a thin wrapper that contacted the HTTP API, but instead we can make that a thick client that actually includes most of the logic that would be happening behind that API. And so at deployment time, that thick client SDK, which has all that logic, gets pulled over into the caller, and it's able to access the resources directly. So all the logic about what that service owns is still owned by the service, but at deployment time is shifted to the caller location.
So it's sort of inlining the function calls.
Essentially, it is essentially inlining. I'd never thought of it that way, but yeah, it's like inlining all of that code. And we still have Lambdas in the services for where they have an API for where they're an entry point from outside the system. So when the app makes a call to the cloud, it's talking to an API that talks to a Lambda that is primarily sort of a wrapper around that thick client SDK for internal inside that one service. And I wouldn't recommend that as a normal pattern. Like, we have unique requirements because of this business model and because of our scale and those kind of things that make this a wise choice. We're looking at, sort of in our next generation of functionality where when it's core to what's happening and going to be in the hot path for a lot of things, we still want to put it in this model where we're avoiding Lambdas calling Lambdas. When you have a Lambda calling another Lambda, you're paying double for that, because while you don't pay for a Lambda function when it's not running, you pay for it while it's running, even if it's waiting for something else. So even if it's not using any resources, you're still paying for it. However, this monolith leads to, it's a restriction on our cadence. It's not something that you can deploy super often. And that's worked very well for us. Like, it's still a model that's working for us and is mature. But as we want to increase the number of features and prototype more features, like a lot of the functionality that goes into that monolith is really the core functionality of the system. And as we have some pieces that are a little more experimental, we're looking for how do we deploy those in independent means, and where are the pain points, the rough edges to individual service deployment and service discovery and authentication and all of those problems that we'll need to solve with that.
There's one other question that I wanted to ask you before we wrap up. You actually talked a bit about it at your serverless conf in New York in a talk called Event-Driven Architectures, Are We Ready for the Paradigm Shift? And it was about reverse Conway's law. So as you're like creating this serverless architecture and you're like kind of putting just the business logic that's out there and leveraging kind of this undifferentiated heavy lifting that the cloud offers, what does that do to like your architecture? Specifically, as I said, you talked about this reverse Conway's law. Can you expand on that a bit?
Yeah, so Conway's law says that your information, the communication patterns in your software are going to mirror the communication patterns in your organization. And when you change from traditional architectures to serverless architectures, you want to change the communication patterns in your architecture to be more event-driven. And what that means is, because Conway's law is a law, that if you don't think about how to make your organization communication patterns match what you want to do now in your software, you're not going to be successful in changing. You're going to end up with trying to fit traditional architectural patterns into a serverless world, and there's going to be, an impedance mismatch there. And so you can build, very synchronous driven serverless services, but it's a more natural fit to think about event driven services, because serverless compute by nature is ephemeral, and events are also ephemeral, right? They represent an instant in time. And so it's useful to think in those patterns of, how do I pass information between services in an event-driven fashion? How do I think in terms of workflows? Instead of thinking about it as, okay, I need to write to a database and then I need to periodically query that database, you think about, okay, well, if someone writes to a database, there's a stream of events that I can listen to be notified when something happens, which broadens what can be considered an API. When you start looking at serverless microservices, sure, there's going to be an API gateway on it that allows you to talk to it over HTTP, but there also may be, a Kinesis stream of events that comes out the back of it that you can hook into to hear about events or an SNS topic. I really like step functions as a model. So this is workflow orchestration, sort of state as a service, which goes hand in hand with, stateless Lambda computation. I think there's something powerful in the idea of sort of federated state machines where, perhaps these state machines or workflows are the part of the API between services to say, all right, here's some event that I can act on in my workflow, and I can wait for that event to come in, or I can fire that event out, and I can hook these state machines together to operate in a collaborative fashion while still maintaining that bounded context between my microservices.
Well, very cool. So let's start to wrap up. We started this off circa 2015. You made a set of decisions based on what the environment was for Lambda and serverless at that time. You solved some problems going forward, but we're 2018. We're looking towards the future. What are still some of the unsolved questions that are out there for serverless that you foresee that we need to address in the upcoming months or years?
Well, one thing that I'm really envious of the Kubernetes folks for is Envoy and Istio, right? That they get this nice service mesh set up by being able to place these sidecars alongside their code and their containers. And in serverless, you don't get the option to have sidecars, right? Your code is only running when it's being invoked. And that means if you put something inside your function to be a sidecar, well, it's only running while the code is running, which means it's going to spend most of its time catching up to what happened while it was off. And so all of these transparent things that are being handled now that people are solving in Kubernetes around creating a service mesh, authentication, authorization, service discovery, these pieces aren't yet solved in a serverless environment. AWS generally now have to think about multi-account environments. And so what does authentication and authorization look like across accounts? Who's defining authorization policies? Is it the caller? Is it the called service? And then doing discovery as a service using something like AWS's parameter stores is a question for, across accounts. How do you notify? How do services find other services? For it to work as a serverless system, we need it to not require a lot of operations work. We need it to be relatively hands-off, and we need providers to be handling most of the heavy lifting there. And right now, you can cobble it together from existing services, but it's not to a point where it's easy, it's out of the box, it's something that you can just sort of plug and play. But at the same time, exactly what it should look like is an open question. So it's not something that I feel that providers can yet act upon, and we in the community need to do more work in figuring out what is it that we want? What does it look like? And so I think that's the next big step in serverless.
Well, Ben, thanks for joining us on the InfoQ podcast.
Thanks again for having me.